Hello everyone, I'm Toshiro Sakuraba, a member of Meiwa Senior High School SSH Chemistry Group.
I am Mariko Sakakihara. Today I will serve as an assistant to him.
First, I explain about my research briefly. I got interest in the fact that metallic ions could be decreased by cation exchange resin. It consists of polystyrene sulfonate. I attempted to synthesize it from waste in everyday life. I used dairy products container made from polystyrene. And I attempted to synthesize it from waste in everyday life. I used dairy products container made from polystyrene, and I succeeded in synthesizing simple cation exchange resin. I also investigated the efficiency of the product made through the synthesis. I found the result satisfactory. I'll tell you about the motivation. A senior member of the club studied about calcium ion and magnesium ion in drinking water. Seeing the study, I wondered if metallic ions in solution could be decreased easily. I examined and found that it can be done with cation exchange resin, but it is too expensive to use frequently. That's why I want to synthesize simple cation exchange resin. The objective is synthesizing cation exchange resin by sulfonating dairy product container and investigating the efficiency of the product. I use dairy products container like this picture. I will introduce an earlier study and compare it with mine. First, in the earlier study, they dissolve polystyrene foam into acetone and add concentrated sulfuric acid to sulfonate it. On the other hand, in this study, I powder dairy product container and add concentrated sulfuric acid. Second, in the earlier study, they confirmed the efficiency of the product by measuring pH through exchange of cation ion. On the other hand, in this study, I checked the decrease of metallic ions in solution directly. I set the hypothesis that polystyrene can be used as cation exchange resin by sulfonating it if polystyrene is powdered, though the reaction between polystyrene and sulfuric acid is solid-liquid reaction. I tried to synthesize cation exchange resin. First, I dissolved polystyrene into acetone and made it globe-shaped. Then, I dried them up. I dissolved in order to make the next procedure easy. Next, I powdered the globe-shaped polystyrene with a file. That's how I powdered polystyrene. This is a micrograph of powdered polystyrene. As you can see, the size of the powder is different from 135 micrometer to 500 micrometer. In order to sulfonate polystyrene, I soaked the powder in heated concentrated sulfuric acid for 10 minutes, giving it 40 degrees centigrade. To check the extent of bonding sulfur group, I measured IR spectra. But unfortunately, sulfur group did not exist. So I changed the reaction condition. Time was changed from 10 minutes to 15 minutes. And temperature was changed from 40 degrees centigrade, 70 degrees centigrade. I measured IR spectra again. This time, an absorption peak appeared at 1250 wave number. This means sulfur group has bonded to polystyrene. Next, I did experiments to find the best condition to synthesize cation exchange resin. First, I synthesized cation exchange resin under various conditions, which means temperature and time. Next, I measured the efficiency of them. At this time, I measure the amount of copper ion cation resin can absorb. I explain how I measure the efficiency of cation resin. First, I clamp absorbent cotton and 5 grams of cation resin in column. And let 50 ml of copper sulfate solution, 0.05 mol per liter copper sulfate solution, 50 ml to the column. After that, I got 50 ml of water to boost the copper sulfate solution, which is left in column. Then, I made a volume of effluent 100 ml and measure the concentration of it by absorptiometry. This is the calibration curve of copper sulfate solution I used. I made it in 792 nanometer. This chart shows the amount of copper ion absorbed in cation resin 5 grams with the unit of millimole. Hyphen, this mark means it is unmeasured, and X, this mark means it is immeasurable to be carbonized. High level of efficiency was observed in 50 degrees centigrade 50 minutes or 60 minutes, and 60 degrees centigrade 30 minutes or 40 minutes. 60 minutes is too long a time to wait for the reaction, so I found that 60 degrees centigrade 40 minutes is the most appropriate. I measured IR spectra again. The green line in this picture is polystyrene spectra, and the red one is the spectra of polystyrene sulfonate, which is reagent. And the blue one is the resin I synthesized in 60 degrees centigrade 30 minutes. Ideal condition is 60 degrees centigrade 40 minutes, but this chart shows the data under the condition of 60 degrees centigrade 30 minutes. I enlarged this area. This peak shows sulfur group. As you can see, this peak clearly appears in the spectra of the resin I synthesized. I computed the rate of sulfonation of the resin I synthesized by comparing the size of this peak with polystyrene sulfonate, which is reagent. At this time, I treated these two peaks as standard because they appeared in all these three spectra. Computed like this, the rate of sulfonation of cation resin I synthesized in 60 degrees centigrade 30 minutes is 23.3%. Next, I made the resin absorb calcium ion and magnesium ion in drinking water, which includes much calcium ion and magnesium ion, in order to check the efficiency to various metallic ions. The drinking water I used was compressed, commercially available one. The amount of calcium ion and magnesium ion in solution was measured by gravimetric calculation with EDTA. And the resin I used this time is the resin synthesized in 60 degrees centigrade 30 minutes. Contrast includes 57.1 mg of calcium ion and 18.1 mg of magnesium ion in 100 ml. I poured 50 ml of it to 5 grams of resin. Then the effluent did not include calcium ion and magnesium ion. Next, I poured 50 ml of 0.01 mol per liter hydrochloric acid into the resin, which absorbed copper ion, to check if the resin can be regenerated. Then the effluent includes copper ion. I measured the amount of copper ion which the regenerated cation resin can absorb. This chart shows the result. As you can see, the efficiency of the resin did not fall off. The conclusion is as follows. I could sulfonate polystyrene, though the reaction between polystyrene and sulfuric acid is solid-liquid reaction, and succeeded in synthesizing cation exchange resin. The best condition to synthesize the resin is to solve polystyrene in concentrated sulfuric acid for 40 minutes with a temperature of 60 degrees centigrade. I checked its efficiency with various metallic ions and regenerated by hydrochloric acid. This thing shows my hypothesis was correct. The perspective is as follows. To try to sulfonate not only dairy products container, but also polystyrene waste used in daily life. To examine if it is possible to make smaller powder to improve the efficiency to sulfonation. To try to apply the resin to purify polluted water. To check about failing the efficiency of the resin. The bibliography is as follows. I would like to thank Mr. Shota Kamichito, Doctor of Philosophy, Nagoya Institute of Technology, Department of Light and Materials Engineering. That's all for my presentation. Thanks for listening.
ありがとうございました。それでは質疑応答へと移らせていただきます。ご質問のある方は挙手をお願いいたします。はい、ではマイクをお渡しいたします。
Thank you very much. I'm a science teacher of Kyoto Senior High School. So I have two simple questions. Did you check how much sulfonate group is contained in your resin? Number two, every time, can you prepare same quality of resin?
First question, you answered the how much can I sulfonate the polystyrene? Yes. This the rate of sulfonation of the resin I synthesized in 60 degrees centigrade 30 minutes is 23.3% by computed like this.
So, did you check the structure of your resin, or did you check the rate of sulfonate only by IR?
Yes, only
Okay.
by IR spectra.
Thank you.
And the next question. Well, I think that all these resin only one time. So I don't know that. Sorry.
Okay. Thank you.
ありがとうございます。その他ご質問のある方いらっしゃいますでしょうか。はい、ではマイクをお渡しします。
Thank you very much for your very good presentation. I'm Okamiya, Osaka State University. You have mentioned about the result for the mixture of magnesium and calcium. And my question is, do you have some comment about the selectivity or specificity for your resin? 混ぜてどういう特性になるかっていうことをちょっと調べられているようなから聞くんですけれど、それぞれの金属イオンに対してこのレジン、自分で作られたレジンが特異性といったらいいか、選択性、この金属について高い低いみたいなことについて、なんかコメント、そういうセレクティビティがありそうかどうかっていうことについてコメントがあったら。
特に金属イオンによるこの吸着の優位性のようなものはまだ確認できてません。はい、すいません。
ありがとうございます。それではお時間も参りましたようですので、以上とさせていただきます。愛知県立明和高等学校の皆さんでした。ありがとう